Hi there. It's good to share this quiet with you. In the gentle dim, allow your shoulders to loosen and let your breath find its easy rhythm. Slow in, soft out. Nothing presses tonight. Just a calm room, a warm voice, and the small comfort of being unhurried. Tonight, we'll turn our lantern toward a thought of immense scale, a playful meeting between opposites. We're thinking about the greatest source of heat we know, the magnificent, constant fire at the center of our solar system, the Sunday. And then, we're thinking about the most vital, soothing element on our Earth, our vast, deep oceans and all the hidden water they contain. We will ask this impossible, imaginative question. What if we could gather that incredible abundance of water and place it upon that blazing surface? We won't rush the answer. We'll move like moonlight across a floor, step by quiet step, simply appreciating the wonder of the forces at play. If this gentle journey brings you ease, a soft like and a quiet subscribe, help others find their way here too. For now, let your breath lengthen, your thoughts grow light, and your mind settle like dust in a sunbeam. Close your eyes. The cosmos is waiting, and we'll begin together. Things have been feeling a little warmer on our small blue world. Summers linger, nights don't cool quite the way they used to, and sometimes it feels as if the whole planet is holding its breath in a slow, gentle fever. In the quiet, it can be comforting to imagine impossible fixes, soft, dreamlike ideas that sit somewhere between science and wishful thinking. One of those ideas is this: what if we gathered every drop of water on Earth, every ocean swell, every raindrop, every grain of ice, and offered it all to the sun, as if we were trying to calm a restless star with the largest glass of water in the universe? Would our bright neighbor flicker and cool, even just a little? Or would that mighty fire hardly notice that an entire planet had emptied itself out? Before we can lean too far into that picture, we need to gently understand what we're facing. The sun is not a campfire we can smother. It is the heaviest, most commanding presence in our solar system, the anchor that keeps every planet, moon, and wandering piece of rock moving in their graceful paths. You can think of it as a colossal glowing sphere of gas, mostly hydrogen, quietly shaping everything around it with its gravity and light. If you could somehow line up Earths like glowing beads, side by side, it would take about 1.3 million of our planets to fill the sun's volume. That number is so large that the mind doesn't quite know where to put it. You could stack Earth upon Earth for a lifetime in your imagination, and still, the star at the center would have room to spare. This isn't just a big object. It is the scale on which big itself learns humility. The heat it gives off is just as staggering. On the surface, the sun stands at around 5,600 degrees Celsius, or about 10,000 degrees Fahrenheit. If you tried to compare that to anything in daily life, nothing would really be fair. It's sometimes said that the energy pouring out of the sun every single second is comparable to the explosion of billions of nuclear bombs going off all at once. Not in anger, but in a steady, relentless blaze that has been shining for billions of years and will keep shining long after every human story has gone quiet. Even describing it as a ball of burning hydrogen is only a rough simplification we use to get close to the truth. Inside, the story is more delicate and more beautiful. About 70% of the sun is hydrogen, the simplest and most abundant element in the universe. Around 28% is helium, a lighter-than-air gas that makes balloons float, but here exists in vast, searing quantities. The remaining sliver, just a couple of percent, is made of heavier elements like carbon, nitrogen, oxygen, and a scattering of others. It's a bit like looking at a simple candle and discovering that its flame is made of many carefully tuned notes, all playing together in perfect, invisible harmony. And then there is the distance between us. When you glance at the sun in your thoughts, never directly with your eyes, you might picture it as something close, just beyond the clouds. In reality, it's about 150 million kilometers away, or roughly 93 million miles. That's around 400 times farther than the moon. If you could drive a car straight up at highway speed, you would be on the road for years before you arrived. For comparison, the entire circumference of Earth is only about 40,000 kilometers. Our world is like a tiny loop of road compared to the long, quiet stretch of space lying between us and our star. What burns inside the sun is not an ordinary fire fed by wood or oxygen. Deep in its core, atoms are pressed so tightly together that they fuse, turning from hydrogen into helium. This process is called nuclear fusion, and it is the true heart of the sun's light. Each fusion reaction releases energy, and together, countless reactions create the warm glow that falls on your face on a mild afternoon and the soft light that paints your window panes at sunrise. That is the flame we are imagining pouring water on, not a spark that can be splashed out, but a deep, continuous reaction in the sun's core. It's also true that the sun is slowly changing. Over immense stretches of time, it grows a little brighter, a little hotter. In a human lifetime, this change is too small to notice. The sun's temperature only increases by about 1 degree over a span of 100 million years. That's the kind of timescale where mountains rise and crumble, continents drift, and entire species appear and vanish. And still, the sun has only nudged itself upward by a single degree. So no, the warmth we're feeling now, the trends we see in our own climate, aren't because the sun has suddenly turned up its own heat. The changes unfolding here, on this fragile blue surface, are much more tightly tied to us, to the carbon dioxide and other greenhouse gases we've released into the air, layer by invisible layer. Over many decades, the sun's gentle, almost unchanging output remains the same kind of steady heartbeat it has always been. It's our atmosphere, our thin blanket of gas, that has been thickening and trapping more of that sunlight than before. Still, it can be strangely soothing to imagine an outside knob we might turn. Instead of carefully untangling our habits and technologies, what if we could simply reach out to the sky and dial the sun down by a notch, like lowering the brightness on a warm lamp? It's not how the real physics works, but as a thought experiment on a quiet night, it lets us explore just how powerful both the sun and our own planet really are. So we picture this: every ocean gathered, every lake and river lifted, all the snow on the mountaintops, and the ice at the poles melted and swept upward. From space, Earth would no longer be blue. It would be a pale, dry stone, its water stolen for our impossible plan. That water adds up to a staggering amount. About 71% of Earth's surface is currently covered in it. Broad oceans spreading from horizon to horizon, seas and bays curling around continents, and darker, deeper trenches hiding in the shadows. If you could somehow collect it all, you would end up with roughly 1.3 billion cubic kilometers of water, or about 332 million cubic miles. Numbers like that feel almost too large to carry, so people sometimes break them into quieter images. Imagine Olympic-sized swimming pools, the kind that look big and echoing when you stand beside them. Now picture not 1,000, not 1,000,000, but hundreds of trillions of those pools, all filled to the brim. Around 554 trillion pools, if you'd like a number to rest your mind on. That is what our planet holds in its basins and clouds, a shimmering skin of water so generous that life has flourished in it, and yet thin enough that in the great scale of the solar system, it would be only a delicate splash. Even knowing that, there's a gentleness in realizing that this entire reservoir still pales compared to the star we're thinking about. Our oceans may feel endless from the shore, but compared to the sun, they are like a cup offered to a furnace the size of a world. It's a humbling, almost peaceful thought. Before we hurry to empty those imaginary oceans, though, it's comforting to start smaller, with something that fits in your hand. Instead of all the water on Earth, picture a single, ordinary glass, about 250 milliliters, or 8 ounces, the amount you might sip slowly in the middle of the night. A clear, quiet weight of water. What would it mean to bring just that little glass close to the sun? To even ask that, we need a way to travel. Our spaceship for this gentle experiment is a real one. NASA's Parker Solar Probe. If you could see it up close, you might be surprised by how modest it is. It's roughly the size of a small horse, not a city-sized starship, and it weighs about 555 kilograms, a little more than half a ton. Most of that weight is instruments, antennae, and, most importantly, a sturdy heat shield, like a careful hand raised between the delicate electronics and the sun's fierce light. In 2018, this probe began its long dance toward the sun, looping around Venus again and again, using the planet's gravity to slowly bend its path inward. Over time, it has slipped closer than any human-made object has ever dared to go. On its tightest swings, it comes within about 6.2 million kilometers of the sun's surface, or about 3.9 million miles. In the silence of space, that is almost unimaginably close to such a dangerous star, and yet, on the scale of the sun itself, the probe is still skimming the outer edge of a vast, bright kingdom. You might wonder why it doesn't go closer still, why we can't just point a rocket straight at the sun and rush in. The answer, in a soft, simple way, is that falling toward the sun is harder than it seems. Right now, Earth is not sitting still. It is racing around the sun at about 30 kilometers every second. To drop straight inward, a spacecraft has to slow down enough to stop circling and start falling. That takes an enormous amount of energy, far more than what's needed to nudge a ship from Earth's orbit out toward Mars. Engineers sometimes say that going to the sun requires about 55 times more energy than reaching Mars. So even though Mars feels distant and mysterious, the real challenge is turning our fast, sideways motion around the sun into a slow, steep dive inward. The Parker Solar Probe handles this by taking its time, letting gravity do much of the work, swinging again and again until its orbit finally dips close enough for us to touch the sun's outer atmosphere with our instruments. Now, add to that picture a single quiet glass of water gently stowed on board. It's a small detail, almost trivial compared to the complexity of the mission, but in our imagination, it becomes the heart of the story. One tiny, familiar object being carried into a place no human could survive, heading toward the light that warms every sea and storm on Earth. In your mind, the little glass of water sits tucked safely inside the probe, and somewhere far below, Earth curves away into blue and white. When the moment comes to leave, something slightly strange happens. The rocket does not leap straight forward toward the sun the way a child might imagine. Instead, it seems to push back as if it were launching the wrong way. This odd move is just our everyday motion showing itself. Our planet is already circling the sun at a tremendous speed, around 107,000 kilometers per hour, or about 67,000 miles per hour. We do not feel it. The oceans stay in their basins. The trees stand still in the yard. But that sideways rush is always there, carrying us along like a train so smooth you forget it is moving. If you want to fall inward, toward the sun, you first have to undo some of that sideways speed. So the spacecraft aims a little backward relative to Earth's journey, stealing a bit of our orbital motion. It is a gentle act of unspinning, not a dramatic slam on the brakes. The result is that the probe's path curves, not straight inward, but slowly, gracefully, like a frisbee you throw against the wind. If you have ever tried to toss one and watched it bend in a way you did not quite expect, you have felt a tiny echo of what is happening here, just stretched across millions of kilometers. From the ground, these paths would look like delicate loops and spirals drawn invisibly in space. The probe glides along them for years, slipping deeper into the sun's domain with every orbit. Time passes quietly. On Earth, seasons change, people grow older, new stories begin and end, and far away in the dark, this small machine keeps turning its face toward the light. Eventually, after many careful swings, the probe reaches the closest part of its journey, the point in space where the sun fills its sky more than anything else. Here, the sunlight is not gentle. It is fierce, pressing, a torrent of particles and radiation. The heat shield glows with invisible stress, holding back a storm. In our soft, imagined version of the mission, a small robotic arm unfolds from behind that shield. It moves slowly, unhurried, bringing the familiar shape of a glass into the light. For a moment, there is something almost tender about the image. A single cup of water, held out toward the star, that feeds every cloud and raindrop back home. Then the arm tilts. The water begins to pour, or at least it tries to. In reality, there is almost no time to see a stream. In the span of milliseconds, before the liquid can fall any meaningful distance, the intense heat and radiation rip it apart. The glass's contents do not puddle on any surface. They flash into vapor, then into a thin mist of atoms and ions, swept away and folded into the charged particles already dancing around the sundae. If there is a sound, it would be a brief, soft hiss, the kind you might hear when a drop of water finds a hot pan, but space has no air to carry it, so even that stays in your imagination. The sun does not dim or stutter. Its steady heart of fusion does not notice this tiny offering of hydrogen and oxygen. From far away, everything looks unchanged. And yet, in the quiet language of measurements, something has shifted. If you could ask the probe to weigh the sun with exquisite care before and after that fleeting splash, you would find that the sun is ever so slightly heavier. All that water, turned to vapor and then to stray atoms, is still matter. It still has mass. Once released into the sun's grasp, it is added to the total, not taken away. It feels backwards. At first, we went there with the soft, half-serious hope of cooling the star, and instead we made it a whisper more massive. The scale moved in the opposite direction of our wish. But that is how the universe tends to work. Adding things in usually makes them heavier, even if in stories we imagine that water always tames fire. Compared to what the sun already is, the extra weight of one glass of water is almost not a number at all. It is like placing a single snowflake on top of a mountain. You know it is there, but the mountain does not change. The temperature at the core of the sun stays the same. The fusion reactions continue as they always have. All that effort, all that travel, and the star hardly registers our visit. There is a gentle kind of humility in that. Our small attempt with a single glass feels more like a gesture than a solution, a way of saying hello to the star that has been shining on us since long before humans learned to dream of rockets. But somewhere in the back of your mind, another thought starts to take shape. If a glass is nothing to the sun, what about something bigger? So the imagination zooms outward, away from a cup you could hold, and toward a body of water so large it reshapes maps, Lake Superior. On the border between the United States and Canada, this lake lies like a piece of sky that decided to rest on the ground. Its surface is so wide that standing at one shore, the far side vanishes beyond the curve of the earth. Waves roll and break like those of a small ocean, and storms cross it as if they had their own weather world. By surface area, Lake Superior is the largest freshwater lake on Earth. By volume, it is among the biggest as well. Its waters are deep and cold, storing winter within them well into the warmer months. If you could magically scoop the entire lake into the air and spread it evenly over North and South America, every field, street, and forest would sit under a shallow sheet of water about 30 centimeters deep, roughly a foot, just enough to soak every shoe and swallow every path. That is still only one lake, one basin carved by ancient ice, and yet it is vast enough that whole communities live from its shores, and whole ecosystems depend on its moods. To think of draining it is already unsettling. You picture harbors left dry, boats resting on mud, fish without a home, birds circling in confusion over empty beaches. In our quiet, hypothetical world, we still pause long enough to ask for permission. This lake touches two countries. Laws and agreements wrap around it like invisible fences. You would need both the United States and Canada to say yes, to agree that emptying this freshwater giant is worth whatever comes after. It is a big ask, even in a story. Let's say, gently, that they agree, that the world has grown worried enough about its warming future, that leaders are willing to consider even the strangest plans. Engineers gather around tables, tracing lines on maps. The simplest idea is to carve a channel from the lake to an enormous pipeline, a kind of artificial river made of steel, leading all the way down to a launch site where rockets can carry the water skyward. Perhaps you picture the desert lands of Texas, where real rockets already rise. Pipelines like this exist in another form. They carry oil and gas across continents, hidden under fields and forests. Some can move millions of barrels every day. If you borrowed one of those and filled it with water instead, your great draining could begin. But the numbers here are patient and unforgiving. Even with a pipeline capable of moving several million barrels daily, sending every drop of Lake Superior along that route would take tens of thousands of years, 70,000 in rough estimates. Long enough that glaciers could come and go again while the water still crept through the dark. And that assumes the pipeline is already in the ground. Building it from scratch is another story. Years of planning, years more of digging, welding, laying, testing. Engineers talk in timelines of 5 to 10 years or more for such projects. For a lake this big, the calendar pages would keep turning. It becomes clear that this gentle steel river, however powerful, is too slow for a civilization that feels an urgent need to act. So the idea of the pipeline drifts away like a sketch in the sand, washed smooth by a new wave of thinking. If you cannot rely on a single, slow-moving pipe, maybe you can pull the water harder and faster from the lake itself. That is where pumps begin to enter the picture. Somewhere in the Netherlands, a country that has long lived in close conversation with water, there are designs for enormous pumps, machines built to move rivers out of the way, to keep land dry where the sea would otherwise insist on coming in. Imagine bringing one of those giants here, a pump like the Nijua systems, capable of moving about 1,200 cubic meters of water every second. It is an industrial heartbeat, pulling and pushing more liquid in a moment than many towns use in a day. At that rate, the pump could empty a cubic kilometer of water, a cube 1 kilometer on each side, in about 10 days. That sounds impressive, until you remember how much Lake Superior holds. The lake's volume is on the order of 12,100 cubic kilometers. If one pump works without resting, it would take around 121,000 days to drink the lake dry. That is roughly 320 years of endless, roaring machinery, with generations of people living and dying while the water level slowly creeps down. 3 centuries is better than 70,000 years, but still far from anyone's idea of an urgent response. So the mind does what it always does. When faced with a task that takes too long, it multiplies. If one pump gives you 320 years, then 320 pumps working together could, in principle, do the job in just 1 year. If you built 960 pumps, you could, at least in the comfort of back-of-the-envelope math, lower that to just a few months. 4 months of thunder and spray, and the lake would be gone. On paper, the numbers line up neatly. In reality, each of those pumps needs a home, a pumping station built on solid ground, with foundations, walls, power lines, control rooms, and maintenance crews. Constructing a single large station can cost on the order of $1 billion and take several years of careful work. Now, stretch that out, building not one, but hundreds, nearly 1,000. The cost climbs into realms where the human brain stops picturing money and starts picturing entire national budgets. The time cost climbs too. While some stations are being built, others wait for materials, for permits, for weather to cooperate. The shoreline around Lake Superior begins to look less like a natural border and more like the edge of a vast, ongoing construction site. Forests are cut back, roads are widened, concrete is poured. The lake's quiet, rocky bays fill with cranes and temporary docks. Diesel engines murmur through the night. The living world notices. Birds that once nested in reeds or on silent cliffs find floodlights and machinery where the dark used to be. Some species might adapt, drifting away to new habitats. Others might not find a way to adjust at all. The balance of the ecosystem, tuned over thousands of years of seasons, is shaken in just a handful. In the halls where decisions are made, people argue softly but fiercely. Environmental scientists warn of irreversible damage. Local communities worry about fishing grounds, tourism, drinking water. Indigenous nations speak of relationships with the lake that cannot be measured in money or megawatts. Cross-border tensions simmer because any change to such a shared body of water ripples into treaties and long histories. And yet, in the frame of our story, the pressure of a warming planet hangs over all these discussions like a distant storm. The plan is framed as a sacrifice for the greater good. One lake offered up in the hope of easing the fever of the world, even if only in some symbolic, experimental way. For the sake of following the thought to its end, we imagine that somehow, after years of negotiation and construction, The world agrees. The pumps are built, the stations hum to life. Great pipes dip into the lake's depths like the trunks of mechanical elephants, drawing up cold, dark water and sending it into vast holding tanks, tanker trucks, and, eventually, toward rockets waiting under clear, hot skies. The surface of Lake Superior begins, very slowly, to fall. What was once a single, serene expanse of blue becomes part of a much larger endeavor, an enormous, improbable attempt to gather a piece of Earth and send it toward the star that made it possible in the first place. As the pumps keep breathing in and out, you now face another gentle but enormous question. Once all that water is gathered, how do you move it to the place where rockets can carry it away? The simplest picture is familiar. You might imagine huge tanker trucks, the kind that look like silver cylinders rolling along highways, each one heavy with water. In your mind's eye, they line up along the shore of Lake Superior, engines idling in a low, distant rumble. Hose by hose, valve by valve, they are filled and sent on their way, heading toward the launch fields. At first, it feels almost manageable. One truck, then 10, then 100. You can picture them in a slow procession, winding down long roads, passing small towns and fields, the lake's water quietly sloshing in their bellies. But when you start to work out how many you would actually need, the story stretches far beyond the edges of comfort. To move all the water of Lake Superior this way, you would need something like 53 billion tanker trucks, not 53,000, not 53 million, but billions. If you tried to park them nose to tail, they would wrap around the Earth many times over, a glittering, endless ribbon of metal and wheels. Highways would vanish under them. Cities would be swallowed by traffic jams that never clear. Every spare patch of land would become a waiting lot for vehicles that can never all move at once. It is one of those moments where the numbers quietly tell you no in their own patient language. The plan doesn't just sound difficult, it starts to feel impossible. The world does not have that many trucks, or drivers, or roads. Even if it did, the noise, the fuel, the exhaust, the accidents, the disruption to everything else that needs to move would turn the whole planet into one long logistical knot. So, with a soft sigh, you let that vision go. The idea of pumps and tanker trucks, as grand as it seemed, melts away like mist in the morning. But the water is still there, the lake still slowly draining in your imagination, and your mind reaches for a gentler, more elegant solution. If moving the water to the launch site is too hard, maybe you can move the launch site to the water. Instead of sending oceans of liquid on a long, clumsy journey from the border of Canada all the way down to somewhere like Texas, you can imagine building the rocket pads right where the shoreline lies. A quiet stretch of land near Lake Superior becomes a different kind of harbor, not for ships that float, but for ships that climb. It's a simpler trade. Constructing a launch facility is still a massive undertaking, but compared to rearranging continents' worth of traffic, it starts to look almost modest. You picture tall towers of scaffolding and service arms rising near the water's edge, concrete pads poured like calm, gray lakes beside the real one. Cables snake out to control rooms where screens glow softly in the dark. Instead of highways filled with trucks, pipes reach directly from the lake into storage tanks and then into rockets waiting upright like silver trees. The vehicles you choose for this dream are versions of real ones, towering spacecraft similar to starships, designed for heavy lifting and deep space journeys. Each one, if you strip away the need to come back home, could carry about 250 metric tons of water as cargo. That's a huge amount by human standards, far more than any truck or plane could manage. You can almost feel the weight of that water as a cool, silent presence packed into insulated tanks. But Lake Superior is vast, and even 250 tons is just a droplet compared to the whole. To take every last drop of the lake and send it sunward, your tally of launches grows and grows until it reaches another staggering figure, roughly 48 billion fully loaded ships. 48 billion tall cylinders of metal, each one the size of a building, all needing to be built, fueled, guided, and allowed to fly. The mind tries to stretch around that number and falters. You imagine factories turning out rocket after rocket, day and night, metal echoing, sparks falling from welding torches like artificial stars. You imagine storage yards filled with gleaming hulls, their noses pointed at the sky, waiting for their turn. Even if you had all the money, all the material, all the time, the sheer scale feels like trying to count grains of sand on a beach, one by one. Still, just to see how far this thought can go, you let the story say yes. Somehow, the world manages to build those ships, to keep the launches flowing smoothly. You don't rely on one lonely pad. You spread out a network of 1,000 launch sites, like a constellation of concrete islands. From each one, rockets rise on a precise, relentless schedule. Every 3 seconds, somewhere on Earth, another starship leaves the ground, day and night, for 4 straight years. If you close your eyes, you can almost hear it. The deep thunder of engines, the sharp, rising roar as each ship tears itself free of gravity's grip. The sky is never entirely dark anymore. Trails of flame and vapor crisscross the upper air, writing brief, bright lines that fade and are replaced by others. For 4 years, the planet lives under a constant, distant growl, like a storm that never quite passes. All of that lifting takes fuel, a lot of it. To reach orbit, each starship uses something like 1,000 tons of methane and 4,000 tons of liquid oxygen. Those are not small amounts. They are vast rivers of cryogenic liquid and compressed gas, turned into controlled fire for a few minutes at a time. Multiply those needs by 48 billion, and the numbers swell into almost mythic territory. Tens of trillions of tons of methane, nearly 200 trillion tons of oxygen. And that is just to get the ships up and out of Earth's gravity well, to the safety of orbit. To nudge them all the way inward toward the sun would take even more. You can picture entire regions of Earth reshaped just to make this fuel. Fields are turned into energy farms, forests into industrial sites, coastlines into refineries and liquefaction plants, tankers and pipelines, factories and compressors, all the machinery that would be needed just to feed this fleet of thirsty rockets begin to draw a picture that looks less like a planet healing itself and more like one straining under the weight of its own desperate plan. Still, in the soft light of your imagination, you let the impossible become briefly possible. The fuel somehow exists. The launches happen. One by one, the rockets rise and vanish into the blue, then the black. Their water cargo is tucked away, waiting to be poured into the sun's direction. As these starships leave Earth behind and glide outward into space, they drift closer and closer to the region where the Parker Solar Probe flies. Out there, the sun is not just a bright disk, it is an overwhelming presence. The surrounding space is filled with charged particles, magnetic fields, and light so intense that it can strip atoms bare. Temperatures in parts of this environment can reach around 500,000 degrees Celsius, close to 900,000 degrees Fahrenheit. It's important to remember that in the thinness of space, temperature behaves differently than what we feel in air. But even with that nuance, the environment near the sun is unforgiving. Parker carries a specially designed heat shield, a carefully crafted armor that lets its instruments hide in a pocket of relative safety. Our imagined fleet of starships, built originally to rise from Earth, has no such protection. As they arc toward the sun, their metal skins begin to suffer. The light gnaws at them. Surfaces heat, coatings fail. Structural parts that were never meant to see such extremes start to weaken. There is no dramatic Hollywood explosion here, just a slow, merciless unraveling. Tanks warm until the water inside turns restless. Bolt by bolt, panel by panel, the ships begin to lose their shape. Before they can get close enough to pour neatly onto the sun, they are undone. Their frames sag in the invisible heat and then come apart. Each spacecraft becomes a cloud of debris and vapor, a scattering of atoms swept up by the solar wind. The water they carried boils away into mist, long before it can form any sort of graceful splash. It is another quiet failure, spectacular in scale, but still a failure. The dream of billions of rockets delivering lakefuls of water straight into the sun ends in a haze of scattered materials, with nothing much to show for it but some extra vapor lost in the star's outer atmosphere. You might feel a small, tired smile at this point. Every route you've tried so far has curled back into no. Trucks choke the roads. Rockets melt. Pipelines take longer than history itself is likely to give. And yet, the mind is stubbornly creative. It reaches for something even stranger, something that almost sounds like a child's drawing of a solution. What if, instead of sending countless little containers toward the sun, you created a single, continuous path, a giant hose, stretching from Earth all the way to the star? It's a wild picture. From space, this hose would look like a thin, improbable line connecting our planet to its primary source of light. To make it work, it would need to be about 150 million kilometers long, some 93 million miles, the full distance between Earth and the Sunday. Most of it could be made from advanced materials that can survive the near vacuum and the temperature swings of open space. But the last 10 million kilometers, the segment closest to the sun, would need to be something truly special. A region built from heat-resistant technology, able to stand up to the star's fierce radiance without melting or bursting. It sounds like pure fantasy, and in our real world, it is. But within this gentle thought experiment, you let it exist just long enough to see what it would do. You imagine constructing this hose in segments, floating them up piece by piece, linking them together above the atmosphere, anchoring one end above Lake Superior, and aiming the other toward the blinding disk of the Sunday. At the lake end, the pumps are still at work, but now they have a new purpose. Powered by something as mighty as a dedicated nuclear reactor, they push water into the base of the hose with incredible pressure. Instead of filling trucks or rocket tanks, that water becomes a long, continuous stream, racing along the inside of the conduit, guided through the emptiness of space. Inside the hose, there is no air, no wind, just the invisible push of pressure driving the water forward. Closer to the sun, the heat-resistant section begins to glow with the hidden stress of what it must handle. Eventually, the far end of the hose opens into the sun's outer atmosphere, and the stream bursts out, turning almost instantly into vapor and ions as it meets the star's environment. Back near the sun, the Parker Solar Probe continues its careful dance. Its instruments are tuned to catch subtle changes in the solar wind, in brightness, in the way the star's outer layers behave. As the stream of water from Lake Superior begins to arrive, not as liquid anymore, but as extra hydrogen and oxygen fed into the sun's vicinity, Parker's readings shift just a little. To your surprise, the sun doesn't dim. It brightens. Its outer layers grow a shade more active. The energy output Parker measures ticks upward by a tiny amount, as if someone had tossed fresh kindling onto an already roaring fire. It feels strange at first, like the opposite of what your bedtime intuition expected. You thought water might soothe the sun, the way a bucket thrown on a campfire sends up a hiss and a cloud of steam, turning orange flames into quiet smoke. Instead, the star seems to respond more like a forge to a new delivery of fuel. To understand why, you let your thoughts drift back to something more familiar. The ordinary fires you've known all your life. A candle on a table, a campfire under the trees, the pale blue flame from a gas stove in a calm kitchen. These fires are born of chemistry, not of the extreme physics inside a star. In a regular fire here on Earth, what's happening is called chemical combustion. Tiny, invisible rearrangements are taking place among the atoms in the fuel and the atoms in the air. Carbon in wood, gas, or coal combines with oxygen to form carbon dioxide. Hydrogen in the fuel joins with oxygen to form water vapor. The process releases heat and light as bonds are broken and new ones are formed, and we experience that release as warmth on our skin and a glow in the dark. For these fires to keep burning, three things have to stay in balance. There must be fuel logs in a campfire ring, gas in a line, charcoal in a grill. There must be oxygen, carried freely in the air around us, and there must be a certain amount of heat, enough to keep the chemical reactions going. If any one of those three is taken away, the fire falters. When you throw water on such a flame, two gentle but effective things happen. First, the water absorbs heat as it warms up and turns into steam. That pulls energy out of the fire, lowering its temperature. If the temperature drops below a certain point, the chemical reactions simply cannot proceed fast enough, and the flame collapses into smoke and embers. Second, the water can form a physical barrier, wrapping around the fuel or spreading over it, blocking the air and reducing the amount of oxygen that can reach the hot surface. With less oxygen available, there is less for the carbon and hydrogen to combine with, and the fire loses one of its three necessary ingredients. So, in your everyday world, water is a gentle enemy of flames. It cools them and smothers them. It takes away heat and, in its own quiet way, steals their breath. But the sun is not an ordinary fire. And as your thoughts turn back toward that distant star, you begin to sense why pouring water into it would not calm it at all. Inside the sun, what's burning isn't wood or coal or gas. It's the tiny, hidden structure of matter itself. Deep in its core, the temperature and pressure are so extreme that light atomic nuclei, mostly hydrogen, are squeezed close enough together to merge. This process is called nuclear fusion. Every time two nuclei fuse, a little bit of mass is turned into energy, and the light and heat we feel are just the gentle surface of that transformation. This doesn't happen a few times a second. It happens in uncountable numbers every moment. Billions upon billions of fusion reactions, like a vast orchestra playing a piece so loud and deep that no human ear could ever truly hear it. A campfire, next to that, is just a single spark, a small warm sigh in the dark. When we imagine throwing water on the sun, we quietly bring along our everyday intuition. We think of bonfires dying under a bucket, orange flames folding into hissing steam. But for the sun, water is not an enemy. Under its intense heat and radiation, water doesn't stay liquid for even an instant. It is ripped apart into its building blocks, hydrogen and oxygen. And hydrogen, ironically, is exactly what the sun loves. It's the main fuel its core has been using for billions of years. So instead of calming the fire, a stream of water becomes a delivery of fresh fuel. Oxygen may go its own way, joining other processes in the star's atmosphere, but hydrogen finds its place in the great internal reservoir. It doesn't suddenly rush to the core and change everything at once, but given enough time, it simply becomes part of the supply the star will eventually use. You might wonder if this extra hydrogen could push the sun towards some kind of sudden disaster, a runaway blaze that tears it apart. The answer is quietly reassuring. No. The mass of hydrogen already inside the sun is so enormous that anything we add from a lake, or even many lakes, is barely a whisper against a storm. If there is any change at all, it's far too small for us to feel. Still, the mind is rarely satisfied with a little. Once it has pictured a lake, it is tempted to ask about everything. If one great bowl of water can't do much, what about all the water on Earth? Every ocean, every cloud, every glacier. If all of it could be poured into the sun, surely that would matter, wouldn't it? To go that far, we have to imagine something even more drastic: draining the oceans themselves. The seas hold about 97% of all the water on our planet. The rest locked in ice, pooled in lakes, flowing in rivers. Hiding underground is just a small remainder. If the goal is truly every drop, then the oceans have to go. This time we skip the notions of trucks, rockets, even hoses. Instead, we lean fully into science fiction. A portal, a doorway that links Earth directly to the Sunday. Not a journey made by vehicles, but a hole in space where water can simply fall through. In this imagined plan, the portal sits at the deepest place in the ocean, Challenger, deep in the Mariana Trench. There, the sea floor lies about 11 kilometers below the surface. The water above is heavy and cold, and the pressure is more than 1,000 times what you feel at sea level. Sunlight never reaches that depth. It is a place of darkness and quiet weight. Building anything there would already be incredible. Building a doorway to the space around the sun feels like something beyond even our most ambitious dreams. But in this gentle thought experiment, we let it exist. We make the portal only about 10 meters wide, large for human eyes, tiny for an entire planet's worth of water. When it opens, water begins to rush through. It pours out of the deepest point in the ocean, slipping through the invisible threshold and emerging far away near the blazing star. The global sea level starts to fall, but at first, the change is painfully slow. Even with enormous pressure feeding the flow, the size of the opening is small compared to the sheer volume of the oceans. Each day, the surface might drop less than a centimeter. Beachfronts creep outward grain by grain, so slowly that a single human lifetime could pass without anyone ever seeing a dramatic change. So the design shifts again. If one doorway is too small, more are added. The original portal is widened, or new ones are sunk into other deep places around the world. At the sun's end, matching outlets are arranged around the star, letting the drained water spill into its outer layers. The ocean system becomes a vast network of slow, orderly drains leading down and out of the world we know. Far away, the Parker Solar Probe keeps circling the sun, its instruments watching the changing conditions in the star's outer atmosphere. When the first water arrives, no longer liquid, but vapor and stripped atoms, its readings twitch slightly. There is more hydrogen in the mix now, more material for the sun to work with. Still, the star does not flare wildly or dim. It accepts the gift with the calm of something already unimaginably rich. The extra fuel nudges its mass upward by a tiny fraction. Its brightness may rise by a whisper's worth, but from Earth's distance, no one would ever see the difference by eye. For all the drama down here, the numbers remain quietly lopsided. The total mass of Earth's oceans, vast as they feel, is only about 0.02% of the planet's own mass. And the Sun? It is about 330,000 times more massive than Earth. Feeding it all of our water is like offering a single droplet to a mountain. The mountain doesn't notice. Back at home, the cost of this experiment is written everywhere you look. The blue of Earth fades. From space, the swirling deep colors of the oceans vanish, replaced by browns, grays, and chalky whites, where seafloors and salt flats now lie exposed. Ancient coastlines are etched into the rock like scars, marking where the water once rested. The oceans, which once cradled life for billions of years, have become enormous empty basins. The remains of coral reefs rise into open air, brittle and skeletal. Shipwrecks sit uncovered, rusting in the sun. Creatures that could not escape plankton and whales, sharks and turtles, are caught in a world that no longer suits them. What was once a thriving, layered ecosystem turns into something more like a silent grave. On land, people scramble to understand what they have left. They count the water still locked in ice at the poles and on mountaintops, and the water hiding underground. All the water the portals didn't touch adds up to about 3% of the original total, something like 11 million cubic kilometers. It sounds enormous, and in a way, it is. When they compare that number to how much water humanity currently uses, roughly 5,000 cubic kilometers each year for farming, industry, and daily life, the first impression might be relief. On paper, there seems to be enough for many centuries, but the paper doesn't tell the whole story. Not all of that 11 million is easy to reach. Much of it is frozen solid in ice sheets and glaciers, or buried deep in aquifers that are difficult and expensive to tap without causing new damage. Melting all the ice at the poles is neither simple nor wise. It would reshape coastlines again, shift climates, and release other long-buried problems. If we focus only on the more accessible part, the water in lakes, and some portion of what flows on the surface, the number shrinks dramatically. Fresh water in lakes amounts to roughly 93,000 cubic kilometers. At a use rate of about 5,000 cubic kilometers a year, even if nothing else went wrong, that supply would not last for 20 years. And of course, everything else would be going wrong. Without oceans to act as giant, slow-moving heat buffers, Earth's climate would swing more violently. Days would grow hotter, nights colder. Wind patterns would warp. Places that once had gentle, moist air would find themselves baking under an unforgiving sun. Any remaining water would evaporate faster, lost to the atmosphere, or locked up in strange, brief storms. The sea breezes that once softened afternoons vanish. The steady currents that used to move warm and cool water around the globe no longer exist to smooth out extremes. A world without oceans does not simply become dry. It becomes unstable, harsh, and unfamiliar. Without the oceans, water falls out of its quiet, hidden role in our climate. It no longer moves heat around the planet, no longer smooths out the wild swings between day and night. There are no deep currents carrying warmth from the equator toward the poles. no cold streams slipping back in return. The great blue basins that once stored both heat and memory are empty, and the air above them has nothing to lean on. Without those oceans, there's nowhere for much of our excess carbon to hide, either. In the world you knew, part of the carbon dioxide we released would dissolve into the sea, changing the chemistry of the water, but at least keeping it out of the sky for a while. Now, with those sinks gone, more carbon stays aloft, wrapping the planet in a thicker, tighter blanket. The greenhouse effect, once muted slightly by the sea's patience, grows sharper and harder to escape. The water cycle itself, evaporation, clouds, rain, rivers, begins to unravel. With almost no open water to evaporate from, clouds become rare and uneven. Some places might still get brief, violent storms, as any remaining lakes and soils give up their moisture. But gentle, predictable rainfall fades, fields dry out. Forests, already stressed by heat and lack of water, become tinder. Fires start more easily, from lightning or from the smallest spark, and they spread without mercy. With rain cycles broken, there is nothing to cool the air or soak the ground. Trees die, then burn. Animals flee as long as they can, but eventually they run out of places to go. In slow motion, across years, the green parts of the planet fade first at the edges, then at the heart. What you end up with is not just one crisis, but several braided together. A climate crisis, because the planet keeps heating and there is nothing left to soften it. An ecological crisis, because the living networks that used to trap carbon, filter water, and shelter life have been disturbed beyond their ability to heal. And a water crisis, because the remaining fresh water is both scarce and unevenly placed, treasured and fought over. The problem you were trying, in some strange way, to solve too much heat trapped around a fragile world has only grown worse. By reaching out toward the sun with oceans in hand, you've stripped away the very systems that once helped Earth stay gentle enough for you. As the changes deepen, temperatures don't just rise by a degree or two. In the hottest regions, afternoon air might reach 60 or even 67 degrees Celsius, around 150 degrees Fahrenheit. That's heat that doesn't just feel uncomfortable. It becomes dangerous for human bodies that cool themselves with sweat that can no longer evaporate properly in thick, stagnant air. If humanity wanted to survive in such conditions, life would have to change in ways that feel almost as extreme as the original plan. Some might try to retreat to Antarctica, where the remaining ice and the lower angle of the sun give a brief, fragile reprieve. Others might dig downward, building underground cities where the soil and rock can mute the worst of the heat, turning homes into sheltered burrows beneath a blistering surface. Living that way would mean letting go of many familiar things: open windows, long walks, farms stretching under the sky. Food would need to be grown in protected spaces, under artificial lights or carefully managed domes. Water would be rationed, recycled endlessly, watched over like a sleeping child. It's a kind of existence that could last for a time, but not forever. Because even with shelters and ice left at the edges, the deeper truth doesn't change. Without oceans to keep a steady water cycle going, without plants to breathe in carbon dioxide and breathe out oxygen, the planet's ability to support complex life slowly drains away. The thin layer of habitability grows thinner still until it is only a memory held by stones and fossils. The one small scientific comfort in all of this, if you can call it comfort, is that the experiment did answer one question. No amount of Earth's ocean water poured onto or into the sun will put it out. The star's fire was never in any real danger from us. As answers go, it's clear, but not very kind, to the world we came from. And yet, even with Earth in ruins in this imagined story, curiosity hasn't quite burned out. One last question rises through the heat, a final, almost stubborn whisper. If our planet's entire supply of water can't do much, what about something truly enormous? What if, instead of draining one world, you could form a ball of water as large as the sun itself and send that to meet it? It sounds impossible because, in every practical sense, it is. There isn't nearly enough water in the solar system to make such a thing. The sun contains about 99.8% of all the mass in our planetary family. Everything else, planets, moons, comets, ice, gas, is just the remaining fraction. Even if you gathered every speck of H2O from every comet tail and icy moon, you'd fall incredibly short. But in this quiet, unrealistic space where thought experiments live, you allow yourself to assume the impossible. Somehow, somewhere, a sphere of water the same size as the sun is put together. It contains about 1 billion times all the water that used to exist on Earth. If our drained oceans felt huge, this new water world makes them seem small and simple. Floating in space, this immense globe of water has an odd kind of beauty. Its surface is in direct contact with the vacuum, where there is no air and essentially no pressure. At that boundary, something strange happens. The water at the surface boils, not because it's hot, but because there's nothing pressing down on it. Molecules escape easily, turning into vapor. But just beyond, in the emptiness of space, temperatures are very low. That water vapor freezes almost immediately into delicate ice crystals. Around the main sphere, a huge, ghostly cloud forms a halo of vapor and frost, constantly replenished by boiling at the surface and constantly frozen by the cold. From a distance, the whole thing might look like a giant, glowing pearl wrapped in a misty veil. Inside, gravity is quietly at work. A ball of water this large has an enormous mass, and that mass pulls inward on itself. The weight of the outer layers presses down on the inner ones. Deep in the center, the pressure grows and grows, squeezing the water into forms we don't see in everyday life. As the pressure increases, so does the temperature. Water molecules in the core begin to move faster, breaking apart into hydrogen and oxygen under extreme conditions. Eventually, the hydrogen at the center could exist not as familiar gas, but as a dense, hot, ionized fluid. If the pressure and temperature climb high enough, the hydrogen nuclei might begin to do what they do inside the sun, fuse into helium, releasing energy. If that happens, then this enormous water sphere stops being just a frozen edges world. It becomes a star in its own right, powered by nuclear fusion at its core. In that case, you haven't created a quiet antidote to the sun. You've created a second Sunday, a new source of light and heat, kindled from a world that started as nothing but water. There is another possibility, though. The pressure in the core might not quite reach the threshold needed to start full sustained fusion. In that case, the object becomes what astronomers sometimes call a brown dwarf, a failed star, too heavy to be a simple planet, too light to shine like a true star. It might glow dimly from the heat of its own compression, but it would never blaze with the steady brilliance of the Sunday. Now, imagine placing this water star, or failed star, right next to our Sunday. If its mass were comparable to, or even greater than, the sun's, the two heavy bodies would begin to dance around each other, tugging and pulling with their gravity. Our familiar star, once solitary, now has a twin to reckon with. As they orbit together, their mutual pull stretches each of them. The sun's outer layers might be drawn out into long, glowing streams, like taffy lit from within. The very core, where hydrogen fusion takes place, could be disturbed by these tidal forces. If the pressure there drops temporarily, the rate of fusion might slow a little. For a brief cosmic moment, the sun's heart could stumble. But as the two massive spheres spiral closer, the opposite could happen. Their cores might be squeezed again by the combined gravity. Fusion could intensify, making the shared system brighter and hotter than ever. It's a complicated, violent waltz, and not one that offers much hope of a cooler, calmer central star. At this point, you reach for the most dramatic idea of all. If simply placing the two suns side by side won't tame them, what if you force them into a direct collision? Not a slow spiral, but a head-on impact, like two worlds rushing toward one another with no intention of slowing down. In such a collision, the violence would be beyond anything we can easily picture. As the water sun and our hydrogen-burning sun slam together, their outer layers would be shredded. Shock waves would ripple through them. For a while, their neatly layered structures would break apart into enormous clouds of hot gas and vapor. Hydrogen, helium, and water, in all its altered forms, would mix and churn. The pressure at the former cores could drop sharply in the chaos, at least for a time. Without enough pressure to keep fusion going in an orderly way, the reactions might slow or pause in parts of the merging system. For a brief, wild interval, the sun's deep engine would falter, but gravity, patient and relentless, would not stop. Eventually, the scattered pieces would begin to fall back together, drawn inward by their combined mass. The clouds would condense again, swirling into a new, larger object. As the gas gathers and compresses, the core heats up once more. Fusion restarts, perhaps stronger than before, inside a star that is now bigger and heavier than the original Sunday. Through all of this, Earth is not a safe bystander. The simple act of adding another sun-sized mass to the heart of our solar system, even before any collision, would twist the gravitational web that holds planetary orbits in place. Paths that were once smooth ellipses would warp, tilt, or break apart. Some planets might fall inward, others might be flung outward into cold, distant darkness. Our world, already dry, hot, and stripped of its oceans and forests in this story, would likely be thrown from its comfortable orbit. It might drift into a path that brings it too close to the new, merged star and burn, or get cast outward into space, freezing slowly as it travels through thin sunlight. Either way, the delicate conditions that once allowed rivers to form and trees to grow would be gone for good. Even neighboring stars, like Proxima Centauri far away, would feel the faint tug of this rearranged mass. Their motions through the galaxy might shift slightly over long ages, a tiny echo of your experiment spreading far beyond the place it began. In the end, every attempt to put out the sun with water, whether from a glass, a lake, an ocean, or a star-sized sphere, leads to the same quiet truth. The sun is far too massive, too powerful, and too deeply rooted in its own physics for us to quench it that way. Water, which feels so decisive against a campfire, becomes almost nothing on the scale of a star. What changes most in all these imagined plans is not the sun, but Earth. Our home is the one that suffers when we strip it of oceans, rearrange its orbit, or tamper with the balance that keeps it gentle enough for life. The star stays, more or less, itself. Maybe the softest lesson in this whole late-night thought experiment is that some problems are not meant to be solved by reaching outward with grand, impossible gestures, but by caring for the small, precious world that's already under our feet. The sun will go on shining for a very long time. What we choose to do with our own thin layer of air and water, while it's still here, is the part that truly belongs to us.